All right. Okay, so then now we're going to talk about valence shell electron pair repulsion theory. There's our next. Is that a mouthful? Try saying that 5 times fast. Try saying that 1 time fast. We call it VSEPR for short. VSEPR. VSEPR for short. Valence shell electron pair repulsion theory tries to tell us something about what shape the molecule is in after it has bonded. And this is important because, as you could guess, when molecules react with each other, they have to come in contact with one another. Because again, just like we saw with ionic bonding, you can't give or receive electrons, whether you're giving them away or whether you're making a new bond, covalent bond. You can't do that without bumping into each other. And when you have 2 atoms bumping into each other to try to make new connections, the angle and the positioning for how they bump into each other actually matters, right? Just like how if you've got 2 people that bump into each other, it's different to accidentally like back up and bump into somebody else who is backing up than it is to like walk forward and walk into somebody else who's also walking forward, right? That has different feeling to it, right? So it's going to be the same thing with molecules. And so we want to know the shape of a molecule. And also the shape contributes greatly to the molecule's physical properties. So physical and chemical properties come from the shape of a molecule. And while our Lewis dot structures that we did up here, they're really good at telling us who owns what electrons and how are they shared and distributed. They don't tell us anything about the shape, right? So I can draw this guy and make it look like it's a line, but that doesn't mean that it is a line, right? I can draw this guy and make him look like he's a T shape or an X. That doesn't mean he is, right? So we need a different model to tell us what shape the molecule is. So valence shell electron pair repulsion theory is actually pretty straightforward in that what it basically says is, look, electrons have negative charges, and we know that same charges or like charges repel one another. So we know that we're going to predict that the electrons surrounding that central atom will repel one another. So that's the ones surrounding the central atom, the ones in its valence shell, or the valence electrons that we just distributed here. If they're bound to something, they have to occupy that space, but otherwise, they're still going to try to repel one another within the sphere that they are at. And here is basically what we know. Because we have to get up to 8 electrons, and they end up as pairs, either as a lone pair, unbonded pair, or bonds, then we have 4 options. I'm not sure if 4 options is exactly right. We have 3 general options here of number of electron sets. So first we're going to count electron sets. A set of electron, you might call it, I think your book might call it a charge cloud. That sounds weird to me. I always learned it as electron sets. A set of electron is a group of electron that belongs to an atom. And we have 3 options here. You can have 2 electron sets, you can have 3 electron sets, or you can have 4 electron sets, right? And so depending on how many electron sets that you have, you can predict, oops, I'm going to keep this black here. We can predict the electronic geometry. And that is to say, I'm going to predict the geometry or the geometric, oh geez, how do I say this? I can predict the spatial arrangement of those electron sets. That's what I mean by geometry here. So the arrangement of those electron sets in space, I can predict just knowing how many electron sets there are. And it's very simple. You just say, okay, I've got some central atom here. And if I have only 2 sets of electrons, and those sets are repelling one another, here's our key. They want to be as far apart from one another as possible, but they still have to be connected to that central atom, right? Because they're owned by that atom. So to be as far apart from one another as possible, they're going to be on opposite sides of that atom, right? You might put a charged cloud of electrons there and a charged cloud of electrons there. We call them electron sets. But that way they are as far apart from each other as they can be while still being attached to that central atom. So this is going to be linear if I've got 2. By electron sets, oh, this is a good question. So Nicole says, by electron sets, you're talking about bonds, right? And the answer is, ooh, well, actually, yes, and I should be specific on this. So I'm glad that you asked this question because I did not clarify that sufficiently. So electron sets means any bonding interaction and any unbonded pairs of electrons. Each of those counts as one set. So I say bonding interaction instead of a single bond because a double bond counts as a single electron set. And a triple bond is a different kind of bonding interaction, which also counts as an electron set. So an unbonded pair is going to be 1 electron set. A single bond is an electron set. A double bond is an electron set. A triple bond is also 1 electron set. Does that make sense? Okay, good, good, good. If I've got 2 electron sets, as we saw, that was linear. If we do this again with 3 electron sets, so again, they're stuck on that central atom, but they still want to be as far apart from one another as possible. And so math just tells us if you have 3 things stuck to a position, but they are as far apart from one another as possible, because like they're taking up space or they're repelling one another, then they look like they're pointing to the corners of an equilateral triangle. So you've got like a bond angle here of 180 degrees. I'm never going to test you on bond angles, by the way. And a bond angle here of about 120 degrees because they're pointing towards the corner of an equilateral triangle. And we call this shape trigonal planar because I am like a triangle, but then I'm also flat, okay? And then if I have 4 electron sets, and they want to be as far apart from one another as possible, here's where it gets tricky. In order to correctly model this, I actually have to do it in 3 dimensions. So I can point one direction. Here's how I do it. The straight line is in the plane of the paper, and then the dashed line is like it's going away from you into the paper or into the screen. And then I'm going to draw a wedge here, and that's going to be like it's coming out of the screen towards you a little bit in addition to going that direction. And it makes this shape. Now, that's how they're going to arrange themselves so they can be as far apart from one another as possible. If you connect the corners, that's how they get the name of this shape. Okay, which says it looks like it's a shape with 4 faces, and that's a tetrahedron. So we call this tetrahedral. I was really confused by that for a long time. I was like, why do you call this a trigonal? It doesn't look anything like a triangle. It's because they're looking at connecting those outside edges, and then you see that triangle. So 4 gives you a tetrahedral shape for the distribution of the electrons that are attached to that central atom. Are you guys with me? Oh, we're just not there yet, Erica. Okay, so I've got this program, ChemSketch. It's actually free. You can download it. You have to make an account at the ACD Labs website. But I'm just gonna kind of draw this here. I've got one carbon with 4 hydrogens. I'm gonna show this to you because my drawing is not super fancy, but I can do it here. And I can optimize that for a 3D viewing. Oh, wait. Now I can set it up to rotate. Haha. Can you guys see what I'm seeing? Okay. It's kind of going back and forth between different models. So now there's a space filling model. That's actually how big those atoms are in their connections here. That's how big the molecule is. You could use, I like the wire frame. Actually, it's a little bit easier with a thicker frame here to show. That's showing basically the electrons, the bonds between them. And then that's showing the space filling model kind of superimposed on that. I wanted to show you this because I wanted you to be able to see this in 3 dimensions, and my art skills are not phenomenal. That's why I'm a chemist and not an artist. But I think it helps to see a 3D model that shows exactly what this guy's all about here. So, does that help? Or is that just kind of a fun, fancy tool? Okay, so there's your tetrahedral shape, trying to show it in 3 dimensions. And again, the wedge is the part that's coming towards you, and the dash is the part that's going away from you. And so, like as for here, these are the 2 that are in the paper. This is the wedge, and that's the dash there. Okay, so that is the tetrahedral electronic geometry. Again, I'm just predicting the geometry of the electrons that are attached to the central atom. The electron sets. So the bonding interaction and the unbonding pairs, that's what I'm predicting here. Your book doesn't include this, but I find it helpful because it informs the next piece here that you need to know. Sorry, we're not done. Based on the number of lone pairs being unbonded pairs, I'll say that, unbonded. Based on the number of unbonded pairs, we'll get a different molecular geometry. Now, the molecular geometry is the geometry of the atoms in the molecule. That is as opposed to the electronic geometry, which is the geometry of the electron sets attached to it. Does that distinction make sense? So the spatial arrangement of the atoms in the molecule, that's the molecular geometry. Let's look at a couple examples, and it might make a little bit more sense. But it depends on the number of unbonded pairs, because a bonding interaction is going to connect the central atom to an exterior atom. But an unbonded pair is not connected to any atoms. So if I have unbonded pairs, only if I have unbonded pairs, then the molecular geometry ends up being different from the electronic geometry. If I am linear, it doesn't matter how many unbonded pairs I have, because the molecular geometry will still be linear. As an example, as we saw up here, I'm going to scroll up, this carbon monoxide molecule has, if we say the central atom is the carbon, I'm just going to put this down here as an example. If we say the central atom is the carbon, hopefully you guys can see this carbon has 1 electron set here because he's got an unbonded pair, and 1 set of electrons here because it's a triple bond. You might ask, well, don't those electrons repel each other too? And the answer is, well, no, they still have to occupy the space between the carbon and the oxygen. Otherwise, it's not part of a bonding interaction. And the longer answer is they're held in different kinds of molecular orbitals, which are similar to the atomic orbitals that we studied. But because we didn't want to spend too much time memorizing and applying atomic orbitals, because it's not going to be super useful long term, we're not going to go into that level of detail. But the carbon monoxide, this carbon atom right here, has 2 electron sets because it's got 1 electron set right here in that unbonded pair and 1 electron set right here in that triple bond. So around this position, you could say this electron set here takes up some space, and it's linear around that position. But it doesn't matter here, I've got 1 unbonded pair, whether I had 1 or none. If I have an unbonded pair, now I just have 2 atoms left and 2 points define a line. So this is linear as is, and we'll do some more examples as well. We've got lots of examples to come. If I have 3 electron sets, then I've actually got 2 options. If I have no unbonded pairs, then the molecular geometry is the same as it was previously, trigonal planar, because if I have no unbonded pairs, then every single one of these electrons in the geometry terminates in an atom. So if I'm looking at the geometry of the atoms, it's going to be the same. But if instead I'm looking at the geometry of the atoms and I've got 1 unbonded pair, then it makes a difference. So let me show you what my options are here. If I look up here, SO3, this is a perfect example of something which has 3 electron sets. Can you guys tell me why SO3 has 3 electron sets? Okay, Erica notes the double bond. Yes, the double bond here counts as a single bonding interaction, so that's 1 electron set. And then additionally, we have an unbonded pair right here on the sulfur. That's a 2nd electron set. And then, yeah, we've got a single bond over here, and that's a single bonding interaction. So there's your 3rd electron set. So we have 3 sets of electrons surrounding the sulfur. So we know that those electrons themselves are organized in this trigonal planar shape. So if I redraw this sulfur with 2 oxygens and a lone pair, and I say those things need to be arranged, those 3 electron sets need to be arranged like this, then I'll find a single bond to an oxygen down here, a double bond to an oxygen down here, and then this other line, it's not really a bond per se. It's just saying that this is the direction that these electrons are and that they take up space. I'm going to put a little cloud here, like they're in a cloud. They take up space and repel these other bonds away from them. Okay, so we still have 3 electron sets as shown, and they're still arranged as we predict according to the way that the electronic geometry will do if they repel one another. Does that make sense? Kind of, that's what we predict. Good. So the electrons, as shown in black, do take on this trigonal planar shape. But if I'm looking at just the atoms and not the electrons, so if I'm looking at the black parts, I see the trigonal planar. If I'm looking at the blue atoms, and I just colored these over blue so that they looked a little bit different, then the arrangement of these atoms then doesn't include this piece, this lone pair. Now it's important that the lone pair is there because it's pushing these other guys down, and I have to remember that. But if I'm looking at just the atoms, then the shape of this ends up looking like a bent line. Do you guys see that? So my molecular geometry for SO2 here is going to be bent. And here's our example. Now, typically, we're just going to put a couple dots on top and not give him a bunch of space. But we know that he does take up a bunch of space there. So this is our example of a bent molecule. I'll keep it that big. Now this is different from a trigonal planar molecule that has, or sorry, a molecule with trigonal planar electronic geometry, which also has trigonal planar electronic geometry. A good example of that one is a molecule of sulfur that has 3 oxygens attached. So if I've got 3 oxygens attached, I'll go through this quickly, but it's good practice. So we can do it, let's see, SO3. Sulfur comes in with 6 electrons. I have 3 oxygens here. They each come in with 6 electrons, so I've got a total of 24 electrons to distribute. I'm going to put sulfur in the middle, and I've got 1, 2, 3 oxygens here. Sulfur is central because it's the first one listed, and now I've used up 6 electrons. And now I have to distribute the remaining electrons on the outside atoms first. So 1, 2, 3, 4, 5, 6 to fill up that oxygen. 1, 2, 3, 4, 5, 6 to fill up that oxygen. 1, 2, 3, 4, 5, 6 to fill up that oxygen. 6 times 3 means I added another 18 electrons, and now I'm all out of electrons. So I skip step 4b because I've got nothing to put on the sulfur. I evaluate the structure. Each oxygen has 8 electrons, but sulfur only has 6. So to make that happy, I'm going to move 2 of those electrons in to the center like that. Did everybody follow me there on that quick and dirty Lewis dot structure? All right, Erica, you're with me. Good enough. I got one of you. All right, so now if we look at this Lewis dot structure, we might be tempted to think this looks like a T-shape maybe, but it's not. I have 3 electron sets because I have 1 single bond, another single bond, and then 1 double bond. So I have 3 electron sets here. So they're going to arrange themselves like this, pointing to the corners of a triangle. It doesn't matter which one gets the double bond because they're all identical. And often when I'm looking at geometry, I'm not going to show the electrons on the outer atoms because I don't necessarily need them to show the geometry around the central atom. They're still there, right? So I could put them there, or as I did here, I dropped them. Now, if I'm looking at just the electrons just on the central atom. Again, I'm not looking at the electrons on the exterior atoms because I don't want to know the geometry around the exterior atoms. I want to know the geometry around the central atom. So if I'm looking at just the electrons around the central atom, these black lines, that's where I get trigonal planar. But if I'm looking at the distribution of the atoms themselves, the blue atoms, it's still trigonal planar. They're the same because every electron set terminates in an atom. So that's the difference between SO3 and SO2, where one of them is trigonal planar, one of them is bent in terms of molecular geometry. Also, if somebody asks you what the shape of a molecule is, they're talking about the molecular geometry and not the electronic. Is everybody with me here so far? All right. If you have a question, please don't hesitate to post it in the chat there. I want to make sure that I'm carrying you all with me because, again, everything builds in this chapter. So if you don't get the Lewis dot structures, you're going to be in trouble. But if you don't get the valence shell electron pair repulsion theory, then you're still going to miss the remaining 80%. So this is very important that we get it while we go. Okay. If I'm tetrahedral, I actually have 3 options for a number of unbonded pairs. I could have no lone pairs, I could have one lone pair, or I could have two lone pairs, and that gives us 3 options for molecular geometry. And I think my table here is going to take up too much space. I switched to a larger font, so I was hoping that would make it clearer, but maybe it didn't, I don't know. Okay, again, as we saw with the trigonal planar, if I have no unbonded pairs, then every one of my electron sets terminates in an atom. Therefore, the electronic geometry is the same as the geometry of the atoms. And so if I have no lone pairs, then my molecular geometry is still tetrahedral. And a good example of that was the CH4 molecule that I built here, right? We've got 1 carbon, 4 hydrogens. You can see the 4 bonding interactions counts as 4 electron sets. If I'm looking at just the electrons, and if I'm looking at the balls themselves, those atoms, then of course it's still the same tetrahedral shape. So that's the CH4. And I'll draw this over here. Move this down here. Kind of like this idea of having the blue atoms and the black electrons. So Nicole asks, on the test, will we have to memorize the electron set shape and what shape they will be, the unbounded pairs? Yes, on the test you have to have this whole, we might call it a chart or a table, you'll have to have this memorized. And it's up to you. I try to teach it to you in this idea of logical progression, right? Number of electron sets gives you this logical electronic geometry, and then based on the number of unbounded pairs, you get this shape. But if it's not as logical to you at the start, you might have to memorize it. I totally get that. And then with continued use, it will start to quote unquote make sense. But if you just have to memorize it from the get-go and then move towards that, I get you. That's what I had to do too when I was a student many years ago. Okay, so that's this guy. We've got a great example of something with 4 electron sets and 1 unbundled pair right up here. This guy. Can you guys see how this NH3 molecule has 4 electron sets and one of those is an unbonded pair? I'm going to drag him down here. Okay, it's a little harder because I'm using dots in this structure instead of lines. So if I make it lines instead of dots, you can see how you get lost in the dots. There we go. 3 single bonds, 1 lone pair. That still gives me 4 electron sets. You can count them and they all take up space. And they're going to be arranged according to this kind of a tetrahedral electronic geometry shape, right? So we've got the nitrogen in the middle. And then my lone pair, I'm going to put it up here, although it doesn't really matter where I put it, it's still going to be the same shape. And then I'm going to put a single bond here, and then a single bond going back here, and a single bond going up here. And I will always show it, if it's this kind of shape, I will always show it from this perspective, because it would be the same thing if I put the dots from another angle, but it would be harder to see, right? So I'm going to put it here, and then Erica noted this is the one that gets the shape, we call it trigonal pyramidal. And again, to get that name, what they do is they connect the outer atoms here, right? at the top, and you see this little squat pyramid, but it's a pyramid with a base of 3 of a triangle, instead of like the pyramids at Giza have a base of 4 sides, so that we call that a square pyramid. But this is I guess that goes behind. This is a base of 3, so that makes it a trigonal pyramidal structure. And again, it's common for us to just show those as 2 dots, even though they're taking up space up there. They have orientation and space. We just put those as a couple dots. So that's our 1 electron set, makes it what we call trigonal, sorry, 1 unbonded pair is what I meant. Trigonal pyramidal. So base of 3. This is different from trigonal planar. In planar means it's flat. It really is just like a flat triangle, whereas this is a little puckered thing. You might look at it like a tripod. Basically, it looks like a little tripod. You guys see that? Okay. Now 2 lone pairs on a tetrahedral shape. Let's see if we've done something like that. Oh, I don't see it. All right. Good example of this, classic example of this is water. So if I'm looking at the structure of water and I draw out, let's see, it's got the structure of H2O, and we've got 2 hydrogens, each come in with 1 electron, plus the oxygen comes in with 6 electrons. We've got a total of 8 electrons to distribute. And then we put oxygen in the middle and hydrogen on either side. And we put a single bond so that they're connected. Then I've used up 4 of my 8 electrons, and I've got 4 left. And then I distribute on exterior atoms, but those are hydrogens. They only want 2, they have 2, they're happy. So now I get to put the last 4 on the central atoms like so. And I'm all out of electrons now, so I'm going to evaluate my structure. And I see that each hydrogen has 2, so they're happy, and oxygen appears to have 8, so it's happy. So there's my quick and dirty Lewis dot structure for water, and it makes it look like it's linear, but it's totally not. Because as you see, every bonding interaction and each unbonded pair counts as electron set, and I have 2 single bonds, so that's 2 electron sets. And then I've got 2 lone pairs. They take up space and they repel the others. Those are 2 more electron sets. So I've got 4 electron sets, and 2 of them are unbonded pairs. So then if I take this water molecule and I say, okay, I've got oxygen here and hydrogen and hydrogen. And again, you can choose any one of those 4 positions on the tetrahedron to put those hydrogens, but I'm going to choose to put the lone pairs in the dash. So there's the dash, and here's the wedge. Now if I draw a wedge and a dash, it makes it look like there's a bond to the lone pairs. So it's not common to do that. Again, we're just going to put the dots there. But then you end up, hopefully you can see it's going to have a structure like this, and we call that bent. Now this bent is different from the bent that we got from the trigonal planar electronic geometry, in that the typical bond angle for your interior of a equilateral triangle is 120 degrees, whereas your typical bond angle for the interior of a tetrahedron is about 110. It's actually 109.5. Again, I'll never test you on this. So it's slightly different bent than that bent, just because the bond angle is going to be different, but it is essentially just bent. All right. Does that make sense? I mean, I do understand all of this is like, hypothetically, it makes sense for like a minute, and then I'm going to go try it and be really confused. I get that. We do have a little bit of time to practice, but just kind of roughly, do you guys have any questions on what I've just done here? Yeah, I hear you, Sylvia. Okay, I'm gonna move this screen over and we're gonna practice. I'm just gonna copy and paste from the worksheet here. Oh, that looks so small. Like I need to zoom in a little. Copy and paste from here. Okay. This is from the worksheet, extra practice problems. There's 15 total that are here. And I'm not sure that we've got time to do all of them, but I'm going to draw out a couple that I think might be challenging. And, well, we should probably just do all of them. Let's do this guy because he's got several different atoms and that seems weird. This guy too. This guy because he has a charge. Well, let's just do this whole middle row here. Let's try that. So the first thing I have to do in order to get the correct VSEPR shape, whoops, sorry, as you saw, is I have to have the right Lewis dot structure because otherwise I can't count electron sets and determine how many of those are unbonded pairs. I just can't apply the table unless I have the right Lewis dot structure. So we'll start with this guy, CCl2O, and we're going to practice Lewis dot structures. So carbon comes in with how many electrons, guys? Your turn to help me with these. 4. Good. How many electrons does chlorine come in with? Got 2 chlorines. They each come in with 7. Good. And then how many does oxygen come in with? It's terrible. Perfect. 4 plus 2 times 7 plus 6. There we go. For a total of how many electrons? (24 electrons. Okay. So now we move on to step 2. Which is my central atom? The carbon central, okay. And I know I've got 2 other kinds of atoms here, but we're just going to put carbon in the middle and say he's attached to chlorine, and he's attached to another chlorine, and he's attached to an oxygen. By the way, Cl, that's not a carbon, another carbon and an iodine, that's chlorine. Yeah. So the first one listed is central. Unless it tells you otherwise, and unless it's hydrogen, because hydrogen can't be in the middle of anything. Otherwise, you just look at that first atom and say, oh, carbon's in the middle, because that's the first one listed. Good question, Emma. All right, so how many electrons have I used now just to make this basic structure? Yeah, I've used 6 because I've done. All right, so how many do I have left? Good, we've got 18 left. So now I'm going to switch colors just to keep track of what I'm doing here. Now I distribute, step 4A says distribute on exterior atoms. So I'm going to put how many electrons on this oxygen? Six. 1, 2, 3, 4, 5, 6. How many electrons on the chlorine? Six again. Good. 1, 2, 3, 4, 5, 6. How many on this chlorine? Same. Okay, same thing. Okay, how many electrons have I used now? I mean, how many more electrons did I just use? Yeah, I just used 18 more electrons to distribute. So how many do I have left? 0. Okay, 0 electrons left. So now I move to step 5, which says evaluate the structure. And when I evaluate the structure, I find, is everybody happy? Does everybody have a full shell? No. Who's missing electrons? Good, the carbon is missing electrons. So we have to share, and now, ooh, something new. I get to pick. Do I share from the chlorine or do I share from the oxygen? What do you guys think is best? Oh, good. Erica and Elena both say the oxygen. That's the right choice. That's the right choice. What made you think it should be the oxygen? That just feel right? Yeah, sometimes you're like, oh, it would look weird to be on the chlorine. So that's okay. There's a reason you have those feelings sometimes, and it's just because you've seen something before and you haven't seen something else. But if we go back to the periodic table here, I'm just going to scroll over and scroll up. We can remind ourselves that oxygen usually has 6 electrons and kind of has space to make 2 bonds, whereas chlorine comes in with 7 electrons, just like fluorine, and is kind of going to want to make 1 bond. So if we have a choice, right, like I've got several different atoms, you might go here and look and say, all right, which one is more likely to make 2 bonds, the chlorine or the oxygen? And based on your position in the periodic table, the oxygen is more likely to make 2 bonds. Does that make sense? That's a little bit tricky, but you guys can do it. Okay, now everybody's happy. I've drawn the right Lewis dot structure, and I have to say, what is the shape of this molecule? What is my, oh, let's see, it asks for the number of electron sets and the electronic and the molecular geometry, and then we redraw it. Tuba's got a really great question. She says, what if we use Cl? Is it going to be wrong? And the answer is, nope, it will not be wrong if you, so long as you've got 1 double bond and 2 single bonds. The rest of your answers here in terms of molecular shape and electronic shape will still be correct, although your Lewis dot structure would technically be wrong. I guess the answer is mixed. Is it going to be wrong? The Lewis dot structure would be wrong, but your geometric shape will still come out okay. All right, what do we have here, guys? How many electron sets do we have? Oh, good. Oh, Nicole is there. Trigonal planar. We have got 3 electron sets, so the electronic geometry is trigonal planar. We have no unbonded pairs, so the shape is still trigonal planar. You guys see that? 3 electron sets with no lone pairs, and we're only talking about the central atom again. When I say lone pairs, I don't count anything on exterior atoms. I don't care as much about what's going on with them. So now I can redraw it and say, like they're pointing to the corners of a triangle, put the O on top just for aesthetics, because we like symmetry, right? As a species, symmetry is nice. And we can say this is 3 electron sets. We have trigonal planar electronic geometry, and we have trigonal planar molecular geometry. And you actually, it feels like you've got a lot of space to write this, but I kind of, once you realize how much work has to be done, it doesn't feel like it's enough space at all. So you might take a couple of pages, or you might do kind of a shorthand, do your Lewis dot structure on a different page, however you like. Does this make sense for CCl2O? Okay. The 3 sets, the 3 electron sets, consist of this single bond, that's 1 bonding interaction, this single bond, that's another bonding interaction, and this double bond is the 3rd bonding interaction. Sylvia, good question. She said, which are the 3 electron sets? And those are the 3 electron sets we see specifically surrounding this central carbon atom. Yeah, perfect, no problem. All right, we've just got a couple minutes more, so let's do NOF. All right, if I look at NOF, how many electrons do I get from the nitrogen? How many do I get from the oxygen? how many do you get for the fluorine? What's my total number of valence electrons available here? Right, so I've got 5 from the oxygen plus 6, sorry, 5 from the nitrogen plus 6 from the oxygen plus 7 from the nitrogen. That gives me, as Sarah noted, 18 total electrons available for this structure. All right, that's step 1. Then step 2 says arrange by connectivity. So what is my central atom here? The N is in the middle because that's the first one listed. Super easy to make the mistake of saying, oh, it must just be bonded as it's shown, N-O-F. It's kind of tempting to do that, actually. Just the N attached to the O attached to the F. Don't make that mistake, okay? The N is in the middle. All right, and then step 3, we've got to add single bonds. So how many electrons did I use up to make single bonds there? I used up 4 electrons. Good. How many do I have left? $14 left. Good. We used up 4 electrons because we put 1 single bond here and 1 single bond here. And remember, each single bond represents a pair or 2 shared electrons, right? So there's 4 electrons represented in those 2 single bonds. Okay. Now moving on to step 4, it says distribute remaining electrons. We have 14 remaining. We want to distribute them on exterior atoms until they are full. And so if we do this and we go around and we say, okay, oxygen wants how many more electrons to have a full shell? 6 more, because he's got 2 in that bond. So 1, 2, 3, 4, 5, 6 electrons for that guy. What about fluorine? How many more does he need? Also 6. 1, 2, 3, 4, 5, 6. Beauty. Okay. And so that has used up an additional, how many electrons? Run out of space. Just to fill those shells, I put 6 on each of those. So that used up an additional 12 electrons. I moved to red because I made those red electrons. How many have I got left here? 2 left. So step 4B says put those guys on that central atom. So there they go. And now I have used 2 more electrons and I'm all out of electrons. So now I move on to step 5, which says evaluate the structure. And what do I see when I evaluate the structure? Am I done? No, what's wrong, Tiba? The nitrogen needs 2 more electrons. And now, we have another question. Do I take it from the oxygen to make a double bond to the left, or do I take it from the fluorine and have a double bond to the right? From the oxygen, for the same reason that we did it here, right? Oxygen's in group 6, it's more likely to want to make 2 bonds than fluorine, who's in group 7 and wants to make a single bond. So that is going to be my Lewis dot structure here. Makes it look linear, but it's not really linear. Let's look at this guy. What do we see? How many electron sets have we got? Three electron sets. Good. We've got 1 single bond, 1 double bond, and 1 lone pair. So that counts as 3 electron sets. So my electronic geometry is still trigonal planar. And I do have 1 lone pair here, which means what is my molecular geometry? Perfect. Bent molecular. All right, so if I redraw this in its correct shape here, I'm going to put a nitrogen in the middle, and I'm going to put an O down here and an F down here. And then my double bond to my O and my single bond to my F, and then 2 dots on the top. It's just bent molecular geometry or a bent shape. Now again, your textbook doesn't talk about electronic geometry, so anytime it talks about geometry or shape, it's talking about molecular geometry or shape. But I will be specific. I will be clear as to whether I'm talking about the molecular or the electronic geometry, like in an exam type setting. Okay, I apologize for keeping you just a few minutes over time, but I wanted to do at least a second example here for you guys. Sarah asks, how do you differentiate between bent and bent? And I'm presuming that what you mean by that is, how do you differentiate between these two bents? You don't, you just call it bent. If I ask for the molecular geometry of either one of these, you should just call them bent. If I ask for the electronic geometry of either of these, of course, you'd call one of them trigonal planar, one of them tetrahedral. But otherwise, they're just bent. And we don't worry or get caught up in the bond angle thing here, because actually, depending on the relative size and shape of atoms, that bond angle differs considerably anyhow. For instance, in H2S, which looks exactly like this guy, but with a sulfur in the middle, in H2S, although the tetrahedral bond angle, you expect it to be 109.5, because the sulfur atom is so much bigger than the hydrogen atoms, it's more like a 90-degree bond angle. So there's an example of how your bond angle here can change significantly depending on what atoms you have. So we don't worry about it, we just call it bent. Does that answer your question, Sarah? Yeah. Okay. All right. Have a good day, guys. Have a good weekend. Get tons of practice on this. Your whole first worksheet is covalent structures. You need a ton of practice. Have a good weekend.